Hi guys, kita bertemu lagi. Sekarang we will move to our next chapter, chapter 5 on trusses design. Definition of a truss system. What is truss? Okay, truss is a structure consisting members, or we can call it as an element that takes only tension or compression where there is no bending. Then the members are connected with a gusset joint that is either we can rivet it, bolt it, or we can weld it so that it has only axial forces that induce to these members. The reason behind these axial forces is we have the external loads applied, that their effects are in the form forces applied only at joints. Types of trusses, we have two types. The first one is planar trusses. The second one is space truss. A planar truss is one where all members and the joint or nodes lie within a two-dimensional plane, whereas the space trusses consist of members that join together at the end to form a large and stable three-dimensional structures. A truss is composed from the three basic parts. The first one is the top chord. The top chord is the beam at the top, which is usually in compression. The second one is the bottom chord. Consists of beam at the bottom, which is usually in tension, and the third part is the webs, where this is we call as an interior beams. There are variety of trusses available, and it's depend on the requirement, especially where have a span length or depends on the loading condition. Function of truss system, there are two types of function. The first we use as a bridge, and the second we use as a roof. There are many types of bridge trusses. Here we have the first one called as a Pratt bridge truss. The second one's whole bridge truss. The third is Baltimore bridge truss, and the fourth one is Bailey bridge truss. We also have different types of roof truss. Here we have four. The first one is Pratt roof truss. The second, Fink roof truss. The third type's whole roof truss, and the fourth one is Warren roof truss. Here are a few most common of roof trusses that has a triangular system or interconnected straight structure element that can be found in your home or industrial property or garage. Another example of roof trusses here, from if you can see in the stadium area, this is types of roof truss structure, and here is a for house. And here what I want to show you is this line, vertical line. This is what we call as a purlin, and connected to the top chord of the roof truss. Trusses also been built as part of highway system. Here we have figures of the highway or roads, and this is the bridge trusses, and this is another example. We can find this type of trusses in Papar and Beaufort area. Another example for bridge trusses, this is has a long distance types of roads using the trusses system. Okay, this is what is space trusses look like. So this is all the trusses joined together and forming a three-dimensional system. This is the components that can be found commonly in roof truss. The first is the roof battens, okay, or we can call as a purlin. The second number two is the top chord. Okay, this is we call as a top chord. Number three is a pitching point. Okay, this is the area of pitching point. Four is the bottom chord. Okay, horizontal members. And the five we call as a web or bracing. And the six we call as a fascia. Okay. Loads and reaction forces on roof trusses. Okay, first we need to calculate the total of load on roof and the total load of purlin, and all these two load will combine and put under truss joint. Okay, this is the figure of reaction forces and truss joint loads. Okay, the red one is the reaction forces. Here at joint A we have a horizontal AX and vertical AY, and joint E is given by reaction forces EY. Okay, here we have only one reaction because it's roller types of connection. Okay, the green one is the truss joint loads. Okay, given by FA at joint A, FB at joint B, two forces FC at joint C, FD at joint D, and FE at joint E. Here is the figure shows the truss type. We have a Pratt in triangular shape. Also we have Pratt in rectangular shape. Fin, and this is curve. This is Belgium. Warren. Hole in triangular and rectangular of hole. Okay, here we have types of Pratt truss. Okay, for the triangular, we have the top one we call as a upper chord, and the bottom horizontal member we call as a lower chord. This is the vertical member, and here we have a diagonal member. Okay, for the distance from the pitch on top of the roof to the horizontal line we call as a rise, and this is the total span length from point A to point B for this truss. For rectangular shape of Pratt truss, here on the top members we call as a top chord, and the bottom member we call as a lower chord, and this is the vertical member, and this is the diagonal member. The rise is the distance from bottom to upper chord, and this is the span length from point A to point B. In whole truss, here is the upper chord on the top member of the truss, lower chord at the bottom member of truss, and this is the vertical, this is diagonal, the rise, okay, from top to bottom, and the span from joint direction A to joint direction B. Okay, this is also a whole truss. Okay, top chord is on top, lower chord in bottom members. This is the vertical members, diagonal members, the rise from top to bottom, and the span length from joint forces A to B. For pin truss, we have upper chord at the top of the roof and lower chord at the horizontal direction of members, the span length, and the rise. For Warren truss, okay, similar to previous we have upper chord at top, lower chord at bottom. We have a diagonal. Okay, we don't have vertical members here. And here we call as a rise and the span between the direction crosses. Okay, similar to this, only the shape is different. So we have upper, lower, diagonal, and we have also here vertical members, rise and the span length. In curved truss, we have upper chord. Okay, this the curve we call as upper chord. The horizontal as a lower chord. We have a diagonal members, vertical members, and the rise at the top, center to the bottom, and the span between direction A and B. This is the simplest type of roof truss, okay, where we have upper chord and lower chord, span and rise. This is we call as a king post truss. Here is another type of a truss, K truss we call it. Okay, so many members inside this type of truss. We have vertical, diagonal, upper chord, lower chord. So normally in a truss system, this is the common terminology where we have a vertical internal member, concentrated load, where we calculate the roof load and the purlin loads, and we have a top chord, the sloped internal member, the bottom chord, and this is a concentrated load, and this is the overall span of truss system. Okay, in steel design, there are so many types of members that can be used in truss system. Okay, we can either use the cold form steel section, the angle types, the C-channel types, joist, CHS or SHS. Okay, now we will move on to the design process for truss system. Okay, for the first thing, we need to calculate the loadings and then do the analysis. And then we have to assume that all joints are pin jointed and all loadings on the joint. The checking of design, the first thing is you need to check for the tensile stress. Tensile stress normally occur at the bottom chord and the diagonal members. And the second one, you need to check for the compressive stress. This occurs at top chord and the vertical members. And then after that, you need to analysis of the load-bearing members such as rafter as a continuous beam supported at the nodes and loaded by the pulley. That's all that you need to do for designing the truss system. This is roof design example. The truss to be designed to support a roof which is only accessible for normal maintenance and repair. Here are the roof parameters. The span is 14 meter with 15 degree pitch. The dimension for the truss shown in figure 1, the imposed load is 0.6 kN per meter square. The truss use the hollow section types for all members. The truss is fully welded. Truss analysis is carried out by placing concentrated load at the joint. So all the joints are assumed to be pinned in the analysis and the actual process are carried out by members. This is the figure 1 from the example question, roof schematic. We have a point load FD divided by 2 at A, FD at B, FD at D, G, and FD divided by 2 at H. So here we have a 15 degree pitch and the degree internal at DC is 30 degree and the total span length is 14 meter and each of the span between A to C is 3500 mm. C to D, same span distance. D, G, and EH has the same span distance, which is 3500 mm. At first, we need to determine the loadings. What is the permanent actions? Okay, due to maintenance and services, the self-weight of roof construction is 0.75 kN per meter square. This value we got from the Eurocode 1. Okay, and self-weight of services from Eurocode 1 stated 0.15 kN per meter square. So add these two and we get the total permanent load action is equals to 0.9 kN per meter square. Now variable actions from the question is only given the imposed roof load is 0.6 kN per meter square. So the total imposed load action is 0.6 kN per meter square. Okay, ultimate limit state for partial factor of action for permanent action lambda g is given by 1.35. For variable action lambda g is given by 1.5. Then calculate for design value of combined action for permanent load 1.35 times 0.9 plus the variable load is 1.5 times 0.6. So that we got the total combined action is 2.12 kN per meter square. Then design value of combined action on purlins. We need to check the action on purlin supported by truss for distance at 3.5 meter between purlin center to center. Therefore, the design value is 2.12 from design value of combined actions times 3.5 distance between the purlins divided by the pitch 8 degree cos 15 degree, and you will get the design value action on purlin is 7.68 kN per meter. And then design value for combined action on truss for purlin span of 6 meter. So FD is equals to 0.68 kN per meter times with the 6 meter span. So the FD will go to 46.1 kN. So all the FD point load at the connection joint of truss will be 46.1 kN. Okay, we'll just go through the video link I provided to you in order to help you to understand how to determine the forces in each member at joint A, B, and C. In order to design the top chart is at member AB, BD, DG, and GH. So compare all these members, we see the maximum design force at member AB and GH is equals to 267 kN. No negative here, but we write down the compression. The NED we already calculated, which is equals to 267 kN. Now we try the size for the steel is 100 by 100 by 5 square hollow section in grade S355. Okay, model elasticity in the room code 1, steel grade S355 and thickness from the code 1, you see that is lesser than 16 mm. So the Fy is equals to 355 Newton per m square. Calculate the elasticity, okay, and we get 0.81. And from the section properties of this size, we will get all these parameters. As usual, you need to check the classification of the cross section. You refer to table 5.2. So C equals to 100 minus 3 times 5 is equals to 85 mm. And then C divided by T is equals to 70. So this cross-section test section is under class 3, limit 42E, whereas 42 times 0.81 elasticity equals to 54. So 17 is less than 34, means that the section is at least class 3. Now we need to check the compression resistance of the cross section. You will follow the equation 6.10 for class A. So it is equals to NCRB equals to A times Fy divided by lambda m naught. So this one, all the value already cut from the parameters. So the NCRB compression resistance is equal to 663 kilonewton. And check for the adequacy. So NED divided by the compression resistance. So it's equals to 0.4. So it's less than 1. So it means that the compressive resistance is adequate. Then check for like flexural buckling resistance. Equation 6.5 for class 1, 2 and 3 is equals to lambda z equals to square root of A times Fy divided by NCR. So this equation is equals to LCR divided by Iz times 1 per lambda 1. Okay, we know that LCR is 1 times the length of AB. So LCR is 3500 divided by Iz is equals 15 degree. So it's equals to 3623 mm. Now calculate for lambda 1 is equals to 5 times square root of E divided by Fy. So it's equals to 76.4. Now lambda dash, or this is the equation, okay, square root of Fy divided by NCR is equals to LCR divided by Iz times 1 divided by lambda 1. So lambda dash is equals to 1.23. Check for flexure buckling resistance, determine the reaction factor due to buckling. So refer to table 6.1, 6.2 and equation 6.49. So we'll get this equation from that Euro code. So check, calculate for this P. Okay, following this equation, where is alpha is equal to 0.21, means that you need to use the buckling curve A for square hollow and calculate for the P. So it is equals to 1.36. And then xz is equals to this formula, and calculate for it, so you get the value is 0.52. And the flexure buckling resistance, this equation, so you already got the xz, a and y, fy already know, lambda m1 already know, so the flexure buckling resistance is equals to 345 kilonewton. Check the adequacy, so NED divided by NBRD, so it's less than 1, so means it's adequate. Okay, means that the size that we choose is satisfactory. Okay, that part finished for top shot design, and then we need to check for design at the bottom shot members AC, CE and H. Okay, check the maximum value is 258 kilonewton, is the intention. Okay, for the bottom design forces is equals to 258 kilonewton. Okay, we choose the same size, 100 by 100 by 5 square hollow, 2 by 5 type of straight steel. Okay, and then check for the design is equal to design plastic resistance of the cross section. So the tension resistance is equals to this formula. So we will include all the value inside this formula. So finally you will get the tension resistance equals to 663 kilonewton. It's more than 250 kilonewtons, means that it is adequate. Okay, now in trusses we have internal members, so you need to design the internal members. We found the internal members is BC, EG, CD and DE. From the maximum design compression, BC and EG is equal to 45 kilonewton. Maximum design tension forces in member CD and DE is equal to 87 kilonewton. So maximum length in compression is BC and EG. So the length is 970 mm. We try this type of steel size 70 times 70 times 5 square hollow with flat steel X355. So just follow the same design. previously. Check for the fracture buckling resistance. Check for tension resistance. Okay, is everything adequate means that all the members selected for this size is adequate. The last checking is to check the deflection. The maximum allowable is span divided by 300 mm. So the span for this truss is 14,000 mm divided by 300. So we get lastly 46.67 mm. Okay, that's all for chapter 5. Thank you.